All right, everybody. So this is the Fluvial geomorphology lecture. So here we go. When we think about fluvial geomorphology, what this word is really referring to is the river, and then geomorphology here. Shape, or geo is earth, morphology is shape. So what we can see is, or what we know is the river shapes the land, and the land then shapes the river. It's kind of like an interplay between two of these things. And I think the best way to think about this is the Grand Canyon. Okay, now the Grand Canyon is a river where it's going through this big sandstone area, and it cuts very deeply. It has cut for millennia down, making the deep canyon that we see. So when you look at the Grand Canyon, it's really obvious that the river is shaping the land. Without that river there, the canyon wouldn't be there, okay? But, on the other hand, without the land itself being sandstone, it wouldn't be a deep canyon like that. Because sandstone is easily erodible, as the river flows through there, it cuts very deeply, and then that's why we get the Grand Canyon. That's why we get the river there like it is. Another example of this is the Red River of the North. Okay, so it starts over here in the border between Minnesota and Wisconsin, flows up north into Lake Winnipeg, and then up into Hudson Bay eventually. Now, this is a classic meandering river. We see here that it is definitely, meandering back and forth. It's a single channel. It's going through some pretty small, normal dirt sediment size stuff. But the crazy thing about this river is that it has an extremely low gradient. I grew up in this area, and I grew up right here in Breckenridge, Minnesota, and it is a crazy place of how flat it is. Like literally, you can see the curvature of the earth as a car drives away from you. So when the river floods, it floods for miles, like literally 20 miles on the left bank, 20 miles on the right bank. And again, so the river floods like that because the land has this gradient. The river, though, maintains this river valley and keeps it really flat as the river kind of has meandered back and forth through this area. So again, the river is shaping the river valley, the land then shapes the river. And here is a picture of when it's flooding. It's pretty crazy of how this river will flood. Happened on my 6th birthday when I was a long time ago, 1989, a big flood, and it made me sad. Anyway, my house wasn't this bad, but it was definitely had water in the basement. All right, so when we think about how rivers are flowing, and when we're thinking about fluvial geomorphology, we really need to think of this idea called dynamic equilibrium. So what does this mean? It means, well, there's an equilibrium point, a point of, I hesitate to say balance, but that's kind of oftentimes how it's talked about. But it's a point at which the river kind of, not spatially is what I'm talking about, but let's say river depth, okay? The river is continuously changing in depth, but if you were to look at the average depth along the length of the river, what we would see is it's pretty much always the same. So at a given spot, there might be some river degradation, so the bed of the river goes down. But in another spot, there might be some river aggradation, where the bed of the river goes up. So the average pretty much stays the same. So you can think about it in a spatial sense or a temporal sense, time sense, where for a little bit the river might be on average a little deeper, but it might be a little up, shallower at another time. But over the grand scheme of things, what we see is that the river will be at the same depth for a long time. So the river is constantly changing, but from like a 20,000 foot view, the river looks the same. So here's a meandering river, right? It's meandering all over the place. We can see all of these old meander scars. We can see some oxbow lakes of where the river used to be. Now, 20 years in the future, where is this river going to be? I don't know. 100 years in the future, where is this river going to be? I don't know. But things like, oh, sorry, same with a braided river. So where, this sandbar here is going to go away tomorrow, right? But there'll be another sandbar over here, or another sandbar's over here. So the river is changing, yes, but it's also staying the same when you look at it from far away. I want to skip here to sinuosity. Okay, sinuosity is like the curviness or the wiggliness of the river. Okay, and what it is it's looking at channel distance divided by the down valley distance. Okay, so take this river here. What you've got is the valley is this, the down valley distance is the length, the distance from C to D. In this case, it's just this VL here, right? But the channel distance, the river curves kind of around it, or in this case, it's this channel length, CL, and it's very curvy and it does not follow a straight line. So what we notice is that channel distance should always be at least equal or larger than the down valley distance. And when you divide those, what you get is a number from 1 to infinity. So a completely straight river would mean that the valley length and the channel length are just completely straight, would be 1. Oh, sorry, hang on, my computer is being weird. Okay. And then a highly meandering river, so something, that looks kind of like this, would be at a sinuosity value of 1.5 or bigger. Really, a super meandering river, you might get like 2.5, but not really much more than that. You'd have to have a valley with really fine sediments, and it meanders a really wide river valley where it can meander real far in there. So I wanted to talk about this when we're talking about dynamic equilibrium, because we know that sinuosity is going to change in this scenario. Okay, so we're going to see, in this scenario, we're going to see these meanders change all the time. And how that happens then, when we look at, the river is constantly changing. Yes, individual oxbows will form and disappear. So at an individual spot, we see the river changing. But if you were to look, from a picture from space, the river is going to look the same. And look the same is referring to this sinuosity value. Okay, the river's sinuosity will be the same, but the actual path of the river will change. Now, when we look at how water is actually flowing down the river, what we see is it's really, remember that it's fastest at the top, and then as the water gets closer, as you get closer to the bed of the river, the water bumps into the ground, and then you have more friction, so it's going to be go down to eventually zero as you come in contact with the sediments. So when you look at how the river then is flowing, and when you bring this into a three-dimensional space on the river, what you'll see is you'll have what this causes is helical flow. So right here we got the right bank and the left bank, right? So as the water comes here, it's going to be going fast at the top, and it's going to bump into here the left bank. As it bumps into that left bank, you're going to get some erosion here, And so this is where, see, we got the left bank right here, right? You're going to have that water flowing very quickly at the top, and at the bottom, because essentially the water is flowing straight at this bend, the bottom is going to be flowing slower. So when it hits this bank, where does that quick water actually go? It actually goes down here, and you can see that going down here, and you get a spiral, a helix of water, that the water will mix in this spiral, in this cycle here, but as you lengthen it down into a river, it becomes a spiral. Now the thing is, it's a spiral, going one way, and then as the river and it hits along the right bank, the spiral flips, and it's going the helix depending on when the last river. So when it hits the left bank, it'll be going to the left, but then as it hits the right bank, the spiral flips over to the right. So we see that this the meanders in the river are causing this helical flow. All right, another topic. Which flows faster? Now, pause the video, think about it for a second. But what happens is a lot of people mix up velocity and turbulence. So this river here is a little stream, babbling brook. It's really loud. You can imagine sitting on this rock. You've got water rushing here. It's very loud, but the water actually isn't flowing very quickly. Okay? What happens is you get water quickly flowing down this little waterfall and then sitting in this pool. And it sits. And then it speeds up as it goes down this little waterfall, and then it sits in this pool, sits for a long time and goes real slow. Now, compare that to a big river that has a lot of potential, or, what you have is you don't have a lot of friction. So in the headwaters, you get a steeper slope, so you might think, well, since it's steeper, that water should go quicker. But in big rivers that are generally have less slope, that doesn't necessarily have to happen, but what you see is since the depth is increasing, you have a lot more water that's a long ways away from that riverbed underneath. So that water up here can actually go really, really fast. You also have finer substrates, so the water isn't bumping into a bunch of rocks and then has to stop and go around that before it can go downstream. What you see is rivers actually flow faster because the longitudinal resistance decreases, and the bends in the river get farther apart, so you can get a bunch of water having a bunch of inertia flowing down the river very quickly, and it makes it so that the water just can speed up and is much faster in a big river. So if you go swimming in a big river, it's really tough because you go into the river and swim for 10 minutes, and you might be a mile down from where you actually got into the river. So it's something to be careful about, right? Now, all right, so let's think about what happens with sediment transport, okay? Now, as you have water flowing down, it's also going to be taking up sediments, okay? And there's 3 types of sediments that you get. So the dissolved load, so this is all the salts that are up into, we'll think about total solids in water, right? And then you've got the TDS and TSS. The TDS is like those salts and those really tiny particles that will stay in suspension even if the water stops moving, okay? So that's the dissolved stuff. You have another amount of sediments that are suspended, meaning they'll be in the water, but as you they'll be flowing down the river, but as you stop the water, they fall out, Okay. Then there's a third type of thing that we don't see in lakes, which is bed load. Now, bed load means if you have the bed of the river here, if you got a rock here, it'll kind of just bounce maybe, or just be rolled down the slope of the river. So what we've got here is dissolved load would be up here, you can't see. Suspended load, which are the smaller particles, and then the bed load is the bigger rolling, sliding. Saltation comes from the Latin word, well, I know it in Spanish at least, is saltar, is to jump. So just kind of the rocks, smaller rocks, bigger rocks that are rolling, sliding, and bouncing down the stream. So, oops, sorry. The crazy thing though about how sediments are transported are a little different. So I want you to spend some time with this graph. So what we've got here on the x-axis is particle size from small to big, and then flow velocity from non-moving to moving, right? You might notice this is a log scale. Anyway, what do we got here? Let's just think about you have really fast flowing water. Or, yeah, okay. Think about fast flowing waters, okay? And this is in centimeters per second, so it doesn't matter, right, the scale that much. So as you have water moving and there's going to be sediments up in that, let's talk about the suspended load right now. For gravel, it takes really high speeds of water to keep that up in suspension. So pretty much what you see is, gravel below, what is this number, 2 meters per second is going to sediment out, okay? And then what you see then is this goes down, 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 down. And then, so sand, you don't need as fast of a water, right? And maybe 50 meters per, or 5 centimeters per second, right? So sand will flow relatively easily. But then what does this mean is that clay, bigger to smaller clay particles will stay dissolved no matter how fast, how slow the water is going. Clay will stay up in the water column. So I think this sedimentation line is relatively easy. So when you're in this portion of the graph, it's basically stuff that's too big or water is too slow and it'll sediment out. Now, because though these rocks have inertia, it's a little different. So what we see here is, yes, it makes sense that the erosion line of it takes. So let's take this gravel that I'm not sure what this is, 10 millimeters. Must be what that is. So let's say a gravel piece, a little rock at 10 millimeters. It because it has inertia as it's rolling down or moving down the stream, it doesn't take as much to keep it in suspension, but to erode it in the first place, what we see is it takes a little bit more. So in this portion of the graph, what we see is that this line is a little, the speed at which it takes to actually erode is a little bit higher. So it makes sense where this goes down, but the tricky part is, why does this go up? Okay, and again, remember this is at a log scale too. And what we see is that sand is the easiest to get moving because it's, and so we see a minimum here. But why isn't clay essentially easy to get moving? And that's at this erosion part. What you need is, clay, once it's up in the water column, it will stay and be in transport. But it's actually really hard to get going. And that's because, think about a bunch of Play-Doh, just put a chunk of Play-Doh in the stream. You need water that's really fast to be able to break off those tiny little pieces of clay, of the Play-Doh, before it'll go up into the water column. And what's happening here then is we're seeing, because the clay particles stick to each other, if you have clay to start with, it's actually really hard to erode that off. So one more time, let's go through this graph. You've got a sedimentation zone, transportation zone, erosion zone. And if you have sediment already moving, you notice that as the water slows down, smaller and smaller particles will settle out, but clay will stay in suspension forever. But to get things going, you need to go a little faster than to keep it in suspension. So that'd be in this little transport zone, right? But to actually get it going, to start it moving, you need a flood that has faster flowing water. But then what takes over is the stickiness of the sediments that will stick together over here, thus making the erosion velocity for clay and silt higher than it is for sand. So I'm going to skip that part. So one thing we see is that when river managers think about how a river looks, how the geomorphology, fluvial geomorphology of the river looks, and the river habitat, what they're oftentimes trying to do is look for this pool riffle sequence. You see from a little side view, what you get are these pools, and then a big little conglomeration of gravel or cobble, bigger rocks, and then a pool, and then a riffle, and then a pool. From the top, it would look like here would be the riffle, pool, riffle, alternating between that. Now, here's a picture where you have, here's a little riffle, here's a little pool, here's a little riffle, here's a pool, right? And a lot of the fish people, or even just if they're looking to increase the biodiversity in any way of this stream, people looking to manage rivers will try to make the stream be a pool and a riffle, because a lot of research has shown that the most diverse habitats are these pool riffle sequences. The thing is, a lot of streams are not naturally this way. To have a pool and a riffle is only important where that's what the original stream was like. So I would refer you to PLQ5. There's this really interesting paper to show how a lot of management has gone into making a lot of these streams pool riffle streams, but when they originally weren't that, and it's causing some problems. I'm sorry for this lecture, it's a little disjointed, but usually I do this lecture with an actual stream in the classroom with this little gravel bed, but I can't do that here, so I'm having to bring a lot of different things into this lecture that don't make a lot of sense. So you got to just kind of think of this as separate sections of this lecture. So one thing we see is that dams are really good at slowing down flow, right? Think of this reservoir here. This is Hoover Dam, right? This reservoir here has nothing for flow velocity. And so when you think of this graph, you got essentially zero velocity, so you get everything, all the bigger sediments just falling out, landing on the bottom of the reservoir, essentially filling up this reservoir with dirt, but all but the smallest sediments, all but those clays, are going to be falling out in the reservoir. So think about as the water comes out of this dam, that river is going to be very clear, clean water with no sediments in it. So what the river tries to do is regain its sediment load. So this is kind of tricky. Any amount of moving water, if it has fewer sediments than it should, than it's able to, it will erode stuff from the bed of the river, and that will degrade the bed of the river then. So in dams, what we see is they really slow down that flow, so the water that's coming out here is really clean, well, I shouldn't say clean, but just clear of sediments. And what it can do is then it's called sediment starvation, and then it can really deepen the bed of the river, cut into way down deep, down to the bedrock, and make the river not what it should be. So one way that people have been looking to mitigate this problem is by along the river valley, they just put some sediments, some natural size sediments that you would find in the area, or the type of the sediments that the dam made settle out. So here's a little river that has a dam upstream, and then as the river is flowing down, it can, especially when it floods here, it can pull up these sediments into the river, so it doesn't starve the river of all these sediments and doesn't degrade the river a whole lot. Oftentimes what they'll do is there'll be a big pile of sediments here right at the downstream end of the dam, not Hoover Dam here, but at the downstream end of the dam, and the river can just pull those sediments to replenish the amount of sediments that river has lost in the reservoir. All right, that's it for fluvial geomorphology. Check back later for more videos and lectures.